on, voice is good. Okay. And this is a Tuesday, Thursday class. So Kevin, whenever you want to make an announcement for the debugging bee or the presentation next Tuesday, just go ahead and let me know.
Yeah, maybe I should talk about it.
Yeah, just take a little bit of time today.
I think we're gonna start putting stuff up.
Okay.
Next week.
Yeah, if you have web pages to bring up, you can just go ahead and do it. Go ahead.
I don't got a web page.
Huh?
No, we don't have a web page or anything.
Okay, that's fine.
Okay. I'm Kevin, president of the Computer Science Club, and on next Tuesday, Halloween, we're going to be having a speaker from Amazon visiting our club at 2:15. We're in room 152D, the computer lab over there. We may be changing rooms, but if we do, we'll leave a sign up for you to follow just for this event. So feel free to stop by if you just want to hear what he has to say. He's going to be talking to us about what it's like to work in Amazon, opportunities for student jobs and internships, and all kinds of questions that we can ask him. The only thing that's off limits is like future technology that they're going to be doing in Amazon. Can't talk about that. So yeah, all of you feel free to stop by, and hopefully it'll be educational. All right. What?
All right, cool.
2:15. So 2:15
On
is when
Tuesday.
you'll be there.
Okay. All right. Thank you. It's good to be able to talk to industry people, especially from Amazon. Even though you cannot ask them about what is the top secret, latest and greatest thing from Amazon, I think it's great to ask questions such as how did you get your job? How did you get here? What is your recommendation of what should I study? Okay, mostly computer science and stuff like that. But you can also ask, in addition to getting a bachelor's degree in computer science, what else can you do at this stage that can help you land a job in the future? So those are pretty good questions to ask. Especially, it depends on the not age, but so much, but how recently that person has gotten his job or her job. So that would be kind of relevant, because if that person has been with Amazon for 20 years, I don't think Amazon has been around for 20 years, but for a long time, that person may not remember, all those details of how he or she got a job.
I don't know exactly how long he's been working there. But I do remember being told he was fairly recent.
Okay, so that would be great, because that means that person is going to be about your age, maybe about 4 or 6 years ahead of you.
He's had other jobs before that.
Okay.
In the industry, so.
Yeah, but Amazon is moving pretty quickly, which means they will only hire people who can keep up with their pace. So regardless of age, this person has to be able to keep up with the pace of Amazon, which is what you guys really need to look into, is how do you keep up with the pace of that industry? Because that has changed a lot. When I graduated, okay, so this is the old man talk, right? When I was la 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 la. But when I graduated with my bachelor's degree in 1989 or so, okay, that was a long time ago, before some of you were born. It was easy, okay. If you even from San Francisco State University, which is not well known for computer science or engineering, right? I mean, you guys probably know about which. CSU is well known for computer science, computer engineering, and so on. And San Francisco State University is not even on the map. Okay, they even tried to cut off the entire school of engineering once because it was just not going anywhere. So anyway, I knew people who graduated from San Francisco University, San Francisco State University, SFSU. And they got a job over at HP relatively easily. And the feedback that I got from them, like a few months after they got their job, was, oh, it's boring. I missed the days, that they were in graduate school, when they were in a master's program over at San Francisco State University, because at least they got stuff to do. They said, there's nothing to do at HP. Okay, you literally just sit there. They'll give you some job to do. You get it done really quickly, and then you ask your boss, okay, what else can I do? They go like, just wait. I'll get you something to do later. That has changed, okay? That's not HP now, okay? You know, if you expect it to be like a cushy, really relaxing job at HP, you cannot be more mistaken. Okay, but that whole industry has changed a lot, okay? Things are no longer the same as before. Before, you know, what you learned in school, you know, C, C++, and whatnot, has a really long shelf life. These days, you know, by the time you walk out of the class, it's already outdated. So it's not about what you learn in the class. It is about how you learn to learn that matters. Okay, you have to acquire the skills and also the basic knowledge that will allow yourself to learn new programming languages, new paradigms, and new whatever that you need to learn when you're at your job. You know, if you expect that the school can teach you everything that you ever need to know to get a job, you know, that I think those days were long gone. Okay, I'm not trying to discourage you guys. I'm just trying to kind of paint a picture of what it is like now to work for high-tech companies. Is they're moving really, really quickly. All right, so getting back to our class, okay, and this is your homework assignment. So the homework assignment is giving you a file, okay, sub.ttp.asm. You can just click on it and download it, okay. You can use it as your basis. I want you to implement this in quote-unquote main, because there's no such thing as main, but I do want you to calculate this particular call. Now, it's not one single call, it is one single statement, but it's not a single call. So the question is, how do you do this? Recursive. It's not recursive. It is not recursive because sub is not calling itself. You are using the result of one sub as the parameter of another invocation of sub. So that's the thing, okay? So what you need to do is to figure out, okay, what do I need to do first? Okay, forget about this sub, okay? You're not ready for that one yet. Forget about this one because you're not ready for that either. This one you can do. So what you do is you say, okay, I know how to do this because both parameters are known. One is 6 and one is 4. Cool. So make that call. It will return a value, right? When that returns a value, it becomes the second parameter of the other sub. Okay, so you do all the stuff that you need to do to pass parameters on the stack, and then you specify the other parameter, and then you do the same thing with this one, and eventually you call the third sub. When you call the third sub, the result is automatically put into register A already. So this part, which is A equals to, is implicit. Okay, you don't have to do it because the subroutine automatically returns a value in register A. You are not allowed to change sub itself. So let's go ahead and let me go ahead and download sub.ttp asm. Yep. Go ahead.
I'm thinking to make like multiple set location like labels for it when you recall.
You will need multiple return points. Yes, because you will have multiple calls, and every time you have multiple calls, you will need one return or continuation point per call. So you will have multiple return points. Okay.
There's going to be more than one function.
There's only one function.
Oh.
So this is what the file looks like. The file that is included in your assignment. This is what it looks like. I got my own main. Okay, this main implements something that's really simple. Okay, so if you want to comment, this main really just implements A equals to, okay, comments. It implements A equals to sub, and the first argument is 85, the second one is 125. This is just implementing that. So your subroutine is going to be, or your implementation of main is going to be a little bit more complicated because it is a nested call of sub, but it's not recursive. Do not change the implementation of sub, which is down here. So this one here, you don't want to change this one. Just keep it the way it is. What you do is you change all of these. So from line 3, okay, so from line 3 to line 15, I would say, okay, get those out, okay, you can comment it out and replace that portion with your code to implement what the assignment is asking you to implement. Is that okay? So now you have to think about all the agreements between the caller and the callee. So this is really about understanding the agreement between the caller and the callee. There are three main things that you have to remember, as a part of the agreements. First one is how you pass parameters. They pass on a stack, but in what order? Last parameter pushed first with a higher address. That's one. Two, how do we know the return value of a subroutine that has a return value? If it's a scalar, it is in register A. All integers and all pointers are considered scalar. So in this case, the result of subtraction definitely is scalar. It is returned in register A. Third one. The third one is when you call a subroutine, the caller is responsible to set up the return address as the last thing to push on the stack. The callee, on the other hand, is responsible to make use of the return address, but also clean that up from the stack. Okay, so those are the agreements. Parameters are the responsibility of the caller to clean up, and that's why we see these two inc instructions or increment D instructions, because the 2 bytes used by the parameters, 85 and 125, are no longer useful at this point, so that's why I clean it up. In other words, when your program gets to the halt instruction, the stack pointer should be back to 0. Because it started off with 0, when you're done, it should go back to 0, because your stack should be balanced. So are we doing okay so far with the description of the homework assignment? Yes? No? Sort of? Okay. So in your homework assignment, you can probably anticipate what value is going to be returned. So in this case, 6 minus 4 is 2, 17 minus 2 is 15, and then 16 minus 15 is 1. So that means by the time your code is done, register A should have a value of 1, and register D should have a value of 0. So what is going to stop people from just do a LDIA with 1 and code done? Well, because I'm going to go through your code and I'll substitute all these constants, 16, 17, 6, and 4, with other values to make sure that your program works in those other cases as well. So if you're not making the actual call, your program is not going to work in my test cases. Is that okay? So as long as you're honest and you're just doing exactly what this code is asking you to do, there's nothing to worry about. Yep.
So are we using these numbers to implement the program?
These are just for testing purposes.
Just for testing.
Yeah, but when you turn in your program, these are the numbers that can be kind of stuck in your program. But I will be going in and I'll change those constants to something else to test your program to make sure it does work for other cases.
Well, we can run it with other cases as well.
Oh yeah, definitely. You definitely want to test it with other cases. But if you're honest and you're actually implementing the code here, there's no reason why it should not work with other values. Okay, any other questions? Any other questions about this particular homework assignment? No questions? All right, cool. Did I demonstrate how to do? Yep, go ahead.
The code that you gave us, what is that doing?
What is that doing?
Yeah.
It is coming from a module. So the code that I just showed you is coming from this particular module about parameters and local variables. So when you look up this particular one, this is the code of the caller subtract, okay, and also this is the actual subroutine of subtract in C, and this is the TTP ASM version of that. So I just put those things together. We talked about that in the previous class, because I just watched the video from Tuesday, and at the end of that particular video, this is what we talked about. All right, are there any questions about this part? No questions? Okay. So I added one section, after the last time we met, which is about local variables. So your local variables are basically on the stack as well. Okay, so the important part here is local variables are also allocated on a per invocation basis, which means every time you call the subroutine, that invocation gets its own local variables. So that part is just like parameters because they're on the stack. However, parameters are allocated and initialized by the caller, which makes sense, but local variables are allocated by the called subroutine. So the caller has absolutely no idea of how many or what local variables are used. So as a result, local variables have addresses that are below the address of the return address itself. And the method to access local variables is very much similar to how you access parameters. So what we'll do today is we'll take a look at local variables, we'll take a look at the swap subroutine, okay, that will exchange the values of two local variables. Is that okay? So I will first present the C code, and then we'll take a look at the assembly code corresponding to that C code. So the C code is going to be something like this. Okay, you don't have to copy this because I think we're streaming, and it is just having two integers x, y. You can initialize x to some particular value, 23, and y to some other value, which can be 65. And we call the subroutine swap, but we pass the address of x and the address of y to the subroutine so that the exchange can actually happen. And here's return 0. The subroutine itself, okay, I'm going to use a prototype here for swap. It is expecting an integer pointer, okay, and another integer pointer here. Because in C, we do not have pass by reference. So the only way to allow a subroutine to change something that does not belong to the subroutine is either by global variables, which is a bad idea. Okay, global variables are evil. Okay, just remember that. Every day you wake up, you just tell yourself, global variables are evil. Don't use those. Okay, so here's the actual implementation of the swap subroutine, which is not very difficult. Okay, you have a local variable t. This is one way to do it. There are many other ways to do it, but this is one way to do it. So you can say t equals to whatever px points to, and then whatever px points to get whatever py is pointing to, and then whatever py points to gets t, which is the original value of what px points to. So that's a very typical swap subroutine implementation. So today, all we want to do is to turn these two subroutines into assembly code without using any global variables. Is that okay? So everything is done on the stack. The local variables are on the stack, including x, y of main. The parameters are on the stack. And we'll do all the dereferencing on the lines inside the swap. And we'll also look into how to pass the address of something to swap. Is that okay? Okay. Before we go forward to talk about assembly code, are there any questions about the C code first? I'm hoping that you guys at least got through 360 and still remember how to use pointers and dereferencing and also the address of. Is that right? Okay, all right, okay. So we'll keep this window open, and then we'll try to implement the assembly code on the other side. So I'm going to fire up another mousepad on this side. So main this time is a little bit challenging already because main has its own local variables, and they have to be allocated on the stack. So we'll probably have to do a decrement D and another decrement D. So we can say that the higher one is Y. Okay, this is allocate for Y, and here we can allocate for local variable X. They're on the stack. Now the ordering of local variables is not really that important as long as you are consistent with that order. It's all good. In other words, I can allocate for X first and then Y. Doesn't really matter. As long as I remember which one is X and which one is Y, it's all good. You cannot be sloppy with parameters because parameters is an agreement between the caller and the callee. So that means whatever the callee is expecting is how you want to set up in the caller's code. So that one you cannot be sloppy, but local variables are all inside the subroutine itself. So you can be a little bit sloppy if That's what you want. So now we want to put values into x and y. They're both living on the stack. Okay. So technically speaking, what we need to do is to copy the stack pointer to C, okay, which is a different register. And then the first thing we do is LDIA with 23, which is x, and then we do a ST to whatever we just push on the stack, whatever location we just reserve on the stack. This basically is doing x equals to 23. Is that okay? So as we talk about this, you kind of need to maintain a mental picture of what is on the stack. So right now, there are two locations being in use on the stack. The higher location is y, and then the lower location, which is also what D is pointing to, is x. Yep.
We see this time pointed to x.
Okay, so so if you want to, you can also describe what D has at each point. And at this point, we can also see equals to D, which is, okay, C is D, but D is the same as the address of X. So as a result, by dereferencing C, we are getting to the location of X. Then we do an increment C, and as a result of this, C is now the address of Y, because at the address of Y is 1 byte on top of the address of X. And then we can use another LDI instruction for the 65, and then do another ST instruction. But this time, we want to be sure that we are not using D. Instead, we'll be using C. This one you can use D or C. It's better to stick with C, I guess. Because C is just a temporary version of the stack pointer, so we can modify that without any really bad consequences. So are we doing okay so far with the program up to this point? I just allocated for the local variables x and y, and initialized those two to the values of 23 and 65. Now, if we want to, we can actually just make the program. This is our program, okay? We can test it, because all we want to do is to make sure that at the end of this code here, the stack pointer, which is D, is pointing to location 254, and then we have 23 at the higher location, at the lower location, and then 65 at the higher location. And you can double check that, okay? So it's a good idea to write a program in steps to make sure that you're initializing the stack correctly in main first before you try to pass those addresses to swap. Is that okay? Do you guys want to test it now, or kind of? Let's go in and check it out. It doesn't take much time, so it's a good idea to test it. Okay, so we'll fire up a Logisim. And processor itself. Go back here, go to the shared folder, so we can get to the assembler. Oh, this guy has P310. Assembler. Has anyone tried out the offline way of using a spreadsheet? No? Okay, there's a way to do it. Okay, so okay, so Control A, Control C, go back here and do a Control V, and then we can get rid of this. It's okay to delete, cells in column A, but don't mess around with column B, because column B have computed results that you don't want to kind of change accidentally. So we don't see any errors. We go to RAM file, and then we just download this. Download as, comma separated value, and we'll call this swap. There we go. switch back to the simulator and load image. This is swap. There we go. All right. Well, this is the a portion of that program. So what we'll do is we'll just run the program at full speed. Okay. Now it's done, and then we want to examine memory locations because the stack is in memory. So we want to look at the content of memory, and we can see the last two locations is 4.1. The highest location is 4.1, which is 4 times 16, 64, and then plus 1, which is 65. The 1.7 is 1 times 16 plus 7, that's 23. So we do have 23 and 65 on the stack in the order that we want. Okay. We also want to make sure that register D, which is our stack pointer, is pointing to location 254, which is the last thing that we push on the stack. And we can see that it is FE, which is 254. So this way, we are basically just double checking, that the program is working the way it's supposed to before we go, any further. So now we are going to implement the subroutine. So let me see where that thing is. Just got past it again. There we go. All right, so we are done with this part. Now we're going to implement the call. So when you implement the call, you need to pass not Y, but the address of Y. And guess what? Somebody already has the address of Y right now. Where is the address of Y now? It's in register C. Okay, very cool. Because that means we just have to decrement the stack pointer to allocate a byte for the parameter, and then we are ready to store. Okay, so now we are storing D with C. So this is basically push the address of Y on the stack, because C already has the address of Y. It is indicated here. Cool. If C currently has the address of Y, which is 1 byte on top of X, how do we get to the address of X? The quickest way. Just decrement, right? Decrement C. So we can decrement C. So at this point, C becomes the address of X, because it's just 1 byte below the address of Y. And then we do another decrement D to allocate the space on the stack for the first parameter. Okay, so this is correct because I want to pass the address of Y first. I want to push that first and then push the address of X. So this is in the correct order. STDC, and this is the same thing as pushing the address of X. Are we still doing okay so far with this picture? More or less? Okay. Well, you know what? We can stop here. We can put another halt here, just to make sure that the stack looks right at this point. What are we expecting to be on the stack? We got 65. Okay, the highest location is 65, and then the 23, and then what?
23, 65.
Huh?
23, 65.
No.
No, yeah.
We're passing the address.
Yeah.
So what is the address of Y?
Oh, FE.
The address of Y is FF, which is 255. That is on top of the address of X, which is 254. So that's what we should be expecting on the stack. Is the same as before, a 4.1 and then a 1.7 followed by FF and then FE. Okay? It doesn't take much time to test it. Okay, and this is what I would suggest you guys to do when you're working on your homework assignment, whether it's this time or later on. I would still say it is a recommended approach. Okay, so I make my program slightly longer. Go to the RAM file, download as, comma separate the value, and we'll keep the same name. And then we go back to the simulator. Control R to reset the entire thing, including the content in RAM, because we have a new program anyway. So we load the image again, go back to swap.csv, reopen it, Control K to start the simulation, Control K to stop the clocking. And we also want to examine the memory locations. So go to edit content, and you can see the address of 41 is FF, the address of 17 is FE, and those are the addresses pushed on the stack. Okay, because there's no point in trying to test swap unless we know the right parameters or the right arguments are pushed on the stack. Is that making any sense? Okay, so that's why I'm debugging this program, or testing the program as we go. Okay, just add a few instructions, test it again, add a few instructions, test it again. So now we get into the subroutine. Okay, or we should, that's the assembly code. Okay, so now we can take out this halt, okay, and continue with our code. So right now what we have done is we are passing the parameters on the stack, but the call itself is not done yet. So the next thing we need to do is to do an LDI. We can use register A for that purpose. This is return address 1, okay, in main. So we'll put, this is the way I do it. I immediately define the label and then go back in and insert whatever it needs to go in between. So we decrement D again because we need to allocate another location on the stack to save the return address. Then we do another ST, but this time we use register A. So we're basically pushing the return address on the stack so that when the callee is done, we know where to go back to. But we also want to remember to call the subroutine, because otherwise that kind of defeats the whole point. When we are done, the first thing we need to do is to increment the stack pointer twice, because the parameters that are still on the stack are now useless. Nobody needs those. So you want to increment D twice to deallocate the parameters. Okay. And that will basically conclude the swap itself. Now we get to the return 0 instruction, or the return 0 statement. So technically speaking, we're done. Okay, we can put a halt instruction here. But in terms of being correct, we really should be cleaning up after our own local variables. So that's why we have another pair of increment D instructions here to deallocate not the parameters this time, but the local variables. But the local variables are not from swap. These are from main itself. Is that okay? So I'm trying to make this as clear as possible, that the first pair of increment D, they are for deallocating something for the call itself. The last two increment instructions, they are for deallocating the local variables of main, and they have to be happening in that particular order. Are we still doing okay so far? Because as I wrote the code, it is probably useful to maintain a map of what is on the stack. Okay. So after all this, we can now have a halt instruction in main, and now our focus will be switching to the swap subroutine. So here's the swap subroutine, and every subroutine needs to have a return back to the original code, back to the caller. So I'm just going to do that first. Okay, so we'll do an LD. It has no return value because it's returned in void, which means I can use register A for whatever purpose I want, because it has no special meaning in this case. So I've got an LD A with whatever the stack pointer points to. Okay, so this is to A equals to the return address. I'm not going to use RET_ADDR1 because we don't know what is on the stack. Swap can be called from somewhere else, right? So I cannot say this is going to be RET_ADDR1, which refers to a particular label. We just know whatever is on the stack at this point should be the return address. Now, whose return address? We don't know. The subroutine doesn't know. And then we increment the stack pointer to deallocate the space used by the return address. And then we just do a JMP-A in this case. Now I can use A in this case only because the subroutine swap does not return a scalar value. So register A has no specific meaning in this case. So now we can go back in and make some changes. Actually implement the whole thing. So what should we do at this point? We're at the very beginning of swap, and we have a local variable t. What should we do? Okay, to allocate, right? Okay, so to allocate, we are just doing a decrement d. Okay, so we are now allocating for local variable t. And just as a habit, you want to do an increment d at the very end. Okay, and I'll insert code in between. Now this is just the way. This is my habit of writing code. Is if there's a pair where this is the entry code and this is the exit code, I always type the entry code and the exit code together, and then I would put stuff in between after that. So this way I don't forget the exit code. Okay. Sorry?
You can use C again to...
Oh yeah, C is going to be used again. Whether you want to use C or B, that's up to you. But it's just my own, convention that I would use C as a temporary version of the stack pointer. Okay, so C is pointing to T. Okay, and it is also a good idea at this point to kind of have a mental picture and even put it into comments what the stack should look like at this point. Okay, so right here. Okay, perhaps over here, I'm going to draw the stack. Okay, in a very crude text way, I'm going to draw the stack. So on the stack, what we should be seeing is py. Okay, and then below py we have px. Below px we have the return address. But I'm not using a specific label because we don't know who is calling me. So I'm just going to say some kind of return address is on the stack. And register D, which is our stack pointer, is not pointing here. And then we have one extra push, or one extra decrement here to reserve that space. And this one is for local variable t. So at this point, both C and D are pointing here. Because D was pointing here because of the decrement, but then I copied the value of D to register C, so both C and D are pointing at this point. Okay, this is a good idea, I think, to draw a map to remind yourself, okay, what does the stack look like at this point? Okay, so now that we have all of this done, the next statement we want to implement is to dereference px as a parameter, grab what it is pointing to, and then put it into t. That's going to be quite a few instructions. Because the first thing we need to do is to go, okay, where's px? Px is right here. It is 2 bytes away from where C is pointing to. Okay, so now you can say increment C, increment C. So after these two, C is now the address of Px. Not Px itself, it is the address of Px. So if you refer back to C convention, C at this point as a register, it has a type of int star star, not just int star, because it is not a pointer to an integer, it is the pointer to a pointer to an integer. Okay? There's no such thing as type in assembly language programming, which is good because you can say, so the assembler cannot nag me about type mismatches and stuff like that. But it's also bad because the assembler is not going to nag you. When you dereference one too many times or not enough times, guess what? The assembler doesn't care. It's like, if that's what you want to do, fine. So it's important for us to keep track of the registers. So now that we know C is the address of Px, and we want to dereference twice in this case, right? So now you have to do the dereferencing, which is, okay, well, I don't want to, question is, do I want to destroy C? Because I want C to kind of be around so that I can get back to T, and so on. So I'm not gonna destroy C. So I would do a CPR instead, BC. So B is now the address of the parameter Px. Then I will do the referencing here. So I'll load B with B. So B is now just Px itself, and then we'll do it one more time. So now B is now whatever Px points to. Is that part okay? Because b originally is a pointer to an integer. To get to the integer, we need to dereference twice. And to dereference, you have to use the LD or the ST instruction depending on which direction. If you're trying to retrieve something, you use the LD instruction. When you're trying to store something, you use the ST instruction. Okay, so this is good. But we need, so we have the left-hand side, which is star PX in register B at this point. Now we need to deal with the left-hand side. The left-hand side is T, so we need to find the address of T. Well, let's see. At this point, C is still the address of PX, which is here. The address of T is 2 bytes below that. So decrement C. So now C should be the address of the local variable T, right? So now it's just a ST instruction, store to C whatever B has. So this entire chunk of instructions, actually this entire chunk of instruction is doing that one line of code in C. Is that okay? Sort of? Okay. Then what do? Well, we move on to the next sentence, the next statement, which is a little slightly nastier than the first one, but it's about the same stuff, right? So the first thing we need to do is to retrieve py. Okay, so at this point, C is the address of T. Py is 3 bytes on top of that. Okay, so we'll do what needs to be done here. Increment C, and one more, increment C. So now C is the address of py. And then we do the same thing. We CPR BC. So that B is the address of py. And then we dereference it twice, just like before. Okay, we store B from where B points to. We store to B where B points to. So now P is actually what py is pointing to. And I'm going to put it here too, so that just so that we are clear what register B is representing. Okay, that's our right hand side. The left hand side is kind of the same thing. So what we'll do is we'll decrement C once here, so that register C is now the address of PX, and then we cannot use B anymore. I want to keep B around, so I can modify another register. Well, register A is free, so I can use register A. So I do a CPRAC. So the A is the address of PX. Actually, I don't need to do a single thing, because once I have the address of PX, that's all I need. No, okay, never mind. I do need to dereference once, so we'll put it into A first. So A is now the address of PX, and we dereference it once, okay? So that A is now PX itself, but we don't want to store to PX, which is the parameter itself. We want to store to what PX points to. So we need to do an ST instruction with A, dereferenced, and B is the other one. So now basically we have star PX equals to star PY. Is that okay? Are there any questions? It is tedious, isn't it?
We just stick with the C code. We just stick with C code.
Stick with the C code. See, in the previous semesters, at least a few years back, I was using the i386 instruction set, and some people figure out how to make the GCC compiler. It's not that difficult. Okay, just look up the documentation. So GCC can crank out assembly code. So you can give it the C code, and then say, okay, I don't need the object code in binary. I want to look at the actual assembly code, and it will crank out the assembly code, no problem. There's no such compiler for TTP, not yet. If you want to write your own compiler in this class, I would not object that. Okay, so we're done with the second instruction. Now we move on to the third one. Okay, So C, last time we know, C has the address of px. We look at the map, px is 2 bytes on top of whatever t has. So now we have to just go ahead and say, okay, we need to decrement it twice, okay, decrement C. Now we have to remember to decrement C and not mess around with D, okay? D stays put this entire time, okay? You can also look at this map here and say, but D is always pointing to T, so instead of doing this, you can always just do a CPR, okay? That works too, because D is still pointing to the address of, is still pointing to T, so now C is the address of P, is the address of T, which is pretty easy to deal with, because now we just have to dereference it once so that we can get to the value of T. So you say yeah, a single LD would work. So LD be with the address of C. So C is now just the value of T. Now we move on to the left-hand side. So we need to find out where to find PY. We know what C is now. C is still pointing to T. So we have to increment it 3 times to get to PY, or the address of PY. So here we say increment C, increment C, increment C. So that C is now the address. Oh, used the wrong red letter here. This is B. Now it's the address of come on, PY. There we go. Now, if you want to convince yourself, you can always say C is the address of the return address, and C is the address of helix. Okay, because that way you can actually do the step-by-step counting. All right, so now that C is over there, I don't have any use of register C any further, so I can just dereference using C itself. So we can now dereference it once. C is now just PY itself, because it was the address of PY, now it's just the value of the parameter, which is by itself a pointer. And then we can now do a ST instruction, because we are storing to whatever C points to. So there's the second dereference, but it is used to point out where we are storing instead of where we are loading. And the right-hand side is in register B already. So this will basically do what star PY equals T should do. And we're done. There we go. So are there any questions, at least about the approach, the big picture? I know it is tedious, okay? This is very tedious, but the idea is, do you have any questions about the approach itself? How we compute the address of the parameters, the address of the local variable, and how we dereference, okay, the number of dereferences that we need in order to get the job done. Questions? Yep, go ahead.
So, like, you're not throwing stuff away on the stack, you are incrementally decrementing?
But I'm dealing with C, not D. D is our stack pointer. I never touched the stack pointer. I never touched the stack pointer until here. Then we toss away the local variable T, which is of no use anymore at this point. And then once we retrieve the return address, we toss that away too, because it's the call list or the subroutine's responsibility to get rid of the return address. Yep.
Can you post this whole thing online on Canvas?
Yeah, I can do that.
You did write out very nicely. What's going on?
Well, one way to do this is when you run this code line by line, you basically track down what is happening on the stack and what is happening to the registers, so that you have a picture, of what is going on. It's a little bit difficult to do, but you can do it with a spreadsheet. It's actually doable. All right, so that means we better save this file into a folder that is persistent. So we can put it into processor, I guess. And we'll call this swap.ttpasm. Okay. So it's time to test it to see whether it works or not, right? So we'll go ahead and Control A, select all, Control-C to copy, switch to the assembler spreadsheet, and just paste it over here. Make sure the bar is done. Look for syntax errors and all kinds of other, well, it cannot catch logic errors, but it can catch most of the other errors. No errors, go to RAM file, download as CSV, and we'll save it under the same name. And then we switch to the simulator, reset the whole thing. I just type Control-R on the keyboard. So that resets everything, it resets more than just the reset button itself. Okay. Right click, load image, same file, just click open. This is why I keep overwriting the same file, just for the convenience of this part here. I can just keep reloading swap.csv. This program is not small, okay? By comparison, well, actually it's kind of small. It's only using up about less than a quarter of all the memory locations, so it's not too bad. Okay. So if we feel confident, we can just let it rip, okay? And did I put a halt instruction? I think I did. I'm just going to double check first. Did I put a halt instruction in main at the right point? Yep, I did. Okay. So I can now switch back to the simulator, and I'm ready to type Control-K to kind of run this whole thing at full speed. But I better know what I should be expecting when this is all done, okay? So we're expecting the locations corresponding to local variables x and y to have the values exchanged. So location 255 should have the value of 17 in hexadecimal. Location 254 should have the value of, what's it again? 61 in hexadecimal, because that's the whole purpose of the swap subroutine. But we should also be expecting the register D, which is our stack pointer, to be back to 0. Because it started off from as 0. If I balance my stack correctly, it should be back to 0. So those are the things that I should be expecting, at least that much. Okay. I haven't done this program before, so we'll go ahead and figure out whether it's going to do it right or not. So we go into memory, edit content. The last two locations indeed have the content exchanged. Because you see, 17, that was in the second last location, and then 41 was in the last location. You can see how those two are now exchanged. Okay, and we also, what is happening on the stack here? How come we have two 17s? One of the 17 is T. The other 17 just so happens to be the return address itself. It just so happens that the return address has exactly the same value as one of the parameters, or one of the value of one of the parameters. And just to double check that, okay, because I don't like things to be just by fluke, okay? So we go to the assembler and we check out this address here. So indeed it is 23 in decimal and 17 in hexadecimals. It is just coincidence that the return address also is 17 in hexadecimal. But I don't like to take chances, as I said, okay? I don't want to know that I accidentally put the 17 in the wrong location. That's why I checked. Is that okay? Sort of.
Can you actually take advantage of that when you make multiple calls to, like, for example, if you wanted to swap many times over?
No. Nope, you don't want to take advantage of that. So this program is done. Are there any questions about the code corresponding to this program? I know it's a little bit long and a little bit complicated, but we have at least addressed several issues. We have addressed the issue of local variables. We have addressed the issue of how to take the address of something. And as it turns out, taking the address of a variable is easier than getting the value of the variable, because you have to get the address first before you can get to the value. So this is counterintuitive, because in C and C++, which concept was introduced first? The value of a variable or the address of a variable? The value, right? But in assembly programming, it is the opposite. Until you know what the address is for a variable, you cannot get to the value of that variable. So taking the address of something is actually easier compared to getting to the value of a variable. Okay, so we got that. We look at the whole program from the perspective of the callee or the subroutine, and we learned how to get back to the variables, the parameters. We know how to allocate local variable, t in this case. We know how to dereference a parameter that is passed as a pointer, okay? And that's why we have the double dereferencing, because the register contains the address of the parameter, but the parameter itself is a pointer. So you have to dereference it once to get to the parameter itself, then you have to dereference it one more time to get to the location that the parameter itself is pointing to. Okay? And we also learned the technique of copying the stack pointer to C first, and then we just use C to move around to compute the actual locations of the various items on the stack. So the most important part that I think we should observe is if you look at the swap subroutine, okay, everything from here all the way to the bottom here, you do not see any absolute memory location reference. Nowhere in here do I do an LDI, some register with a constant and then dereference that register. It is all relative, okay? It's all floating with D. Whatever D turns out to be, everything else is relative to D. Is that okay? So those are the kind of important parts to kind of take note of, because there's a lot of detail, but when you kind of take a step back, you look at, okay, what is the big picture? What is interesting about the big picture? So those are the things that are interesting about the big picture. And I have no idea why I'm signed out of my account. So I'm gonna have to sign in again. And it says sign in, but I'm not signed in. So it wants me to actually go to apps. It could be the cookie just expiring on its own. Which is annoying. There we go. Refresh, this time should be good. Yep, we're back. All right. So are there any questions about the swap subroutine, both from the perspective of the subroutine itself and also from the caller's perspective? So we know how to compare, we know how to do swap. So with the introduction of the concept of an array, we can do bubble sort. Well, that's the job of a compiler, right? The compiler is what is turning the C code into assembly code. Depending on which university you're transferring to, when you're done here, many universities, 4-year programs, offer a class in compiler design. So, using your experience in this class of manually translating C code into assembly code, the compiler class, when you're up to that class, will only be about parsing, because you know the code generation end already. You know what you need to track and stuff like that. So it would be mostly just the parsing part that will be kind of the challenge, but not so much oh, what kind of code are we cranking out? We know that part already. Shall we move on? Okay. So if this is done, we're going to move on and use another sample program. But the first thing I'm going to do is to do what I said I would, which is adding that file to this whole thing. So can I add a file? Yep. Okay. So we're going to add a new file, and that's going to be in our processor folder. Okay, just type processor. Go. Inside the folder, we have swap.ttp.asm. Open that, upload it to course files, and item, and it's now here. So it's ready for download for you guys to study. In the next exam, we'll have a practice exam next week for the next one. So I better finish grading the previous one first, right? That would be. Grading is difficult, trust me. It is difficult for me anyway. So this you can print it out. Okay, everything that we do in class. Okay, remember anything can be that you can print or handwrite prior to the test. You can bring it to the test. So that would include all the sample programs that we do in class. Not just this one, any sample program that we do in class, including the solution to all the homework assignments, you can bring those with you. Is that okay? All right. How many people still remember arrays? How to use arrays in C? Okay. Oh, do you want me to copy this one too? I don't think this one is kind of that important. Is that okay? Okay. Just in case you want, we'll do it later. Okay, so if you still remember pointers, or pointer arithmetics at least, let's see how we can do a string compare. I know string compare is not recommended because it is actually not safe, okay? Because you can access memory that you're not supposed to access using string compare as opposed to string and compare, where you say, okay, this is as far as we go, the number of bytes, okay? But string compare is an easier one to kind of conceptualize and implement. So you have two strings, okay? This is string 1, and this is string 2. And we want to, how would you implement this in assembly? How many people do not know what is string compare? Because I can describe what string compare is first before we move on. Everybody knows what is string compare? Okay. Now just to be sure, I know you guys all nodded, but just to be sure, this is what I'll do. So I'm going to go to the man page of string compare, and just to make sure that we are comfortable with string compare. So the string compare function compares the two strings, S1 and S2. It returns an integer less than, equal to, or greater than 0 if S1 is found, respectively, to be less than, to match, or to be greater than S2. Okay? So that means if S1 is less than S2, it returns a negative number. If they equal to, then it returns a 0. Or if S1 is found to be greater than S2, it returns a positive integer. That's basically what it's saying. We're not using string and compare, which is just length delimited, the length delimited version of string compare. The string compare and string and compare function returns an integer, blah, 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 same thing that we just saw a little bit earlier. So, no questions about this?
So
All right. Yep, go ahead.
it compares the values in ASCII or something?
It compares the strings. So that means ABC, all lowercase, is considered quote unquote less than DEF, and it will return a negative value. DEF compared to ABC will return a positive integer. ABC compared to ABC will return a 0. ABC compared to ABCD will return a negative value because ABC is less than ABCD, right? So that's basically how string compare works. Compare strings. Okay? All right. So we focus on the C implementation first. Okay? So the C implementation, okay, if you think about it, is to say as long as they are the same and as long as at least one of them is non-null, keep going. Does that make sense to you? The first statement, or the first sub-expression, okay. Take a look at this sub-expression first. So the first sub-expression, or the left-hand side of the conjunction, says, oh, they're pointing to exactly the same thing, okay, which means I cannot determine the order yet. But we also need the second condition, which is at least one of them is non-null. Well, but if they're the same, and at least one of them is non-null, that means they're both non-null. Is that making any sense? So when do we get out of the loop? We get out of the loop when they are not the same, right? Because that will fail the first condition. Or we also get out of the loop when they're both null. So those are the two conditions that we get out of the loop, is when they are different, when S1 and S2 point to different things, we get out. When they are both null, when they're both pointing to null characters, we also get out. So what should we return? Because by the time we get out, we can see that they're either both the same length and they're identical, or they're different somewhere. This is where things get a little bit funny. That is what we can return. Because guess what? If they are exactly identical, they would both be null characters. 0 minus 0 is 0. That's good. If they're different, then whatever the difference is between these two characters will set the correct sign, because the return value never says anything about returning -1 or 1. It just says negative versus positive. So the difference between these two will set the correct sign. That's all we care. Is that okay? But if you do not like this kind of string compare, and instead you say, isn't there a more elegant way of doing the same thing? Then the answer is yes, you can do it recursively. I'm half joking. You guys are not getting it. Okay, so how do we do string compare recursively? In other words, we are looking at this from the lazy perspective. It's like, okay, I'm doing string compare, but I'm not going to say anything that's politically incorrect. I was about to say something, but I just got okay. So I'm just going to compare. I will only do the comparison of one character. That's all I'm going to do. Somebody else will have to handle the rest. Okay. So that's the premise of recursion, is you handle a very small task. Whatever task is left has the same nature as the task that was given to you, but it is a little bit less complicated. Okay, the size of the problem is smaller. Okay, so that's the whole idea of recursion. But when you deal with recursion, you better figure out a way to end it first. Okay, you have to think about the end case of a recursion. So the end case is really just saying, hey, if this is different, oh, okay, wrong language. If they're different, then I'm done, because I have a conclusion right now. Okay, so your conclusion, okay, is this is just me doing my thing. So result is S1, whatever S1 points to minus whatever S2 points to, and then at the very end you say return result, because I don't like putting a return in the middle of a conditional statement. Okay, the else is saying they are the same. Okay, so we better make this one catch the other one too. Okay, so this one is that or not S1. Okay, that will catch the null case too when they are both null. Huh? Why would this condition? Why would the if condition also catch the case when you have the two strings being identical? They're both null. S1 is pointing to null, S2 is also pointing to null. Why would they catch that? Well, first of all, when S1 points to null and S2 points to null, it will fail the first condition, the condition to the left of the destruction, right? Well, if it fails that condition, it implies one thing. It implies S1, whatever S1 points to, is the same thing as whatever S2 points to, right? So we know it leads that much. But then S1 points to null. Okay, let's put it together. They are the same. Okay, S1 points to the same byte, same kind of byte that S2 is pointing to. They have the same value. But we know one of them is pointing to a null character. Doesn't that imply the other one is also pointing to a null character? If they're both pointing to null characters, then we're at the end of both strings. We have a conclusion. They're the same. Just return 0. Except instead of saying return 0, I say just return 0 minus 0, which turns out to be 0. That works. So this will catch both cases of coming to a conclusion when you're comparing two strings. So that means the else case has to handle the case where, okay, S1 and S2, they're not pointing to null characters, but they're the same character, okay, which means it is not conclusive yet. So what you do is you say result, okay, equals to string compare. This is the recursive part. S1 plus 1, S2 plus 1. Yep.
Could you also do plus plus S1?
You could, but it's better not to change the value of a parameter or a local variable unless you really have to, because because we're just doing recursion, right? So that means we should not be changing S1. We're just passing S1 plus 1 to the next invocation. So this is the recursive version of string compare. Now, the recursive version of string compare is not realistic because it is consuming a lot more stack space than it really needs to, but it is also nice in a different way. How do you prove an algorithm is correct?
Seeing if you can write recursively.
Huh?
By
Why would recursion help in the case of trying to prove the correctness of an algorithm?
Prove the base case and prove that I plus one case is
Yep,
correct.
and there's a name for that kind of a proof. It's called proof by
Induction.
induction. Very good. Okay, so there's a proof technique called proof by induction, and recursive subroutines lend itself to proof by induction. Okay, and that's why sometimes we like to look at things from a recursive perspective, because you can apply proof by induction to prove the correctness of something like this. Okay. Is it practical to actually implement string compare like this? No, not really.
But it illustrates that you can turn a iterative subroutine into a recursive subroutine. All right, we have 5 minutes left. Well, do you think 5 minutes would be enough time to get this done? Okay.
Assembly language.
In assembly language.
No.
What if I tell you that we have enough registers to play with so that we can keep S1 and S2 in 2 different registers? Would that be enough? Do we have enough registers? Not really, because the compare is the issue. The comparison is, we're going to run out of registers because of the comparison. Because if S1 is taking up 1 register, S2 is taking up another register, then what are we going to use for the comparison? Because compare CMP requires 2 registers, but they will be the values that S2 is pointing to, and also the value that S1 is pointing to. So we don't have enough registers for the entirely register approach, which means this is going to be a little bit more tedious than I thought it would be, but it can be done. It's just not going to be as simple as I thought it would be. So we'll defer that to the next lecture. So the next lecture will pick up from this point, and we'll implement string compare using assembly code, and then we'll test it with an actual program. Is that okay? So your homework assignment is due next Thursday. You have 1 week to work on it. And I think I'm going to coincide with the practice test next week. So on next Thursday, we'll have a practice test for exam 2. Any questions? No questions? All right. So I'm going to end the lecture. We are about 3 minutes ahead of time, 2 minutes and something ahead of time. And then we'll transition to the lab for those of you who want to get started with a homework assignment. And you can ask questions. You can ask questions about what we talked about today. And that's it for today's lecture. Let me save the file first so that I have a way to get back to it. There we go.